So now that we've got a bit of a handle on absolute temperature, we'll go ahead and start developing the ideal gas law. Now, what we'll be doing here is defining ideal gases and stating the ideal gas law. It'll be a future video where we prove the ideal gas law. So, to say what an ideal gas is, the main criteria we need are that it's low density. And the reason for that is we need the molecules of gas to interact primarily with the walls of the container. And we need the temperature well above the condensation point. So this here is just to avoid complications of atoms interacting with each other. And this is to avoid the further complication that if we're close to condensing, what will happen is you'll start to form bonds between adjacent atoms, and then that collection of atoms can act like a single object, which would change the number density of particles, and we don't want to mess with that. So in the limit, you think of a bunch of geometric points that are all just bouncing off the container. In practice, I usually think of it as like really tiny BBs bouncing around within the container, and we can ignore the very occasional interaction between the particles. So for now, we'll state but not prove the ideal gas law. So if we have this kind of a gas, it is the case that the product of the pressure and the volume of the gas is equal to the number of particles times Boltzmann's constant times the absolute temperature. Now, in chemistry classes, you will probably have seen this as the number of moles times the ideal gas constant times the temperature. Both are perfectly fine. So Boltzmann's constant, which is actually how we properly define temperature, but it's still going to take me a bit to get there. And by the way, most of the time we usually just write K instead of KB. Is exactly 1.380649 times 10 to the negative 23rd joules per Kelvin. And in the SI redefinition, this is an exact number. If you prefer using the ideal gas constant, the ideal gas constant is Boltzmann's constant times Avogadro's number. And this works out to be exactly, and it's a mouthful because we're just multiplying two exact numbers together until we run out of numbers. It is 8.3144626181532 joules per mole Kelvin. Now, most people are not going to bother carrying all those digits. Usually just say 8.314 and get on with your life. If it helps to remember it, because we will be going back and forth between these two forms. What I always remember is you always have P and V. And then I remember that I always have to have one, in addition to the temperature, I have to have one big and one little letter. So I either have a big N and a little K, or a little n and a big R. Alrighty, so historically, the way the ideal gas law was found was by looking at different ideal gas processes. Now what we will be doing is we will be eventually using Newton's second law of motion to obtain the ideal gas law. So we'll, for now, think of it as true. So the first process we can think of as an isochoric, or it's sometimes called isovolumetric. Process. So this is, since the volume doesn't change, basically what you got here, and this is just an example I can think of. I just stick a thermometer into a vessel. I go ahead and I light a Bunsen burner underneath it like that. And what will happen is the temperature goes up and the pressure goes up, right? But the key thing with all these processes is they'll all start with iso, and iso comes from a Greek root meaning the same. So say the same what? Choric or volumetric, same difference, the same volume. So we know that the volume is a constant. This gives us an opportunity to use a clever trick called scaling. A lot of times in physics you end up with looking at complicated equations, but you realize that a lot of things aren't changing. So for instance, I can write down the ideal gas law. PV equals, we'll use the nRT form this time. Now in this process, for all the processes we're looking at, the number of moles of the gas doesn't change. The ideal gas constant is literally that, a constant. And for an isochoric process, the volume doesn't change. So the only things that could change are the pressure and the temperature. So I'll say P final times the volume would equal NR times T final. Now what I can do is I can divide the left-hand side by P initial times the volume, as long as I divide the right-hand side by that, but I'll write that as nRT initial. So I've written the ideal gas law twice. Once for the final state after I turned on the Bunsen burner, and the initial state before I turned on the Bunsen burner. Now what you do is you just cancel all the common factors. And you end up with P final over P initial equals T final over T initial, and that's Gay-Lussac's law. Now, a lot of times what we'd like to do is we'll draw what are called PV diagrams for this. They're not graphs, even though we make a scale. The reason they're not graphs is what we do is we mark all the pressures and volumes we went through along the way. So we'll mark our initial pressure and volume, our final pressure and volume. Because the volume never changed, the process is just plain like this. We went from initial to final, and we draw a little arrowhead so we know which way we went. So this is telling us that the pressure increased because we started here, went there. All right, let's take a look at another. We can look at an isobaric process. So again, iso, the same what? Bar as in barometric pressure. So the pressure is a constant. So what we can imagine is, say, having a piston. Like so. So we've got some gas under a piston. I go ahead and light a Bunsen burner under this or something. This will cause the gas to heat up, and in the process it will push the piston out of the way. Well, the mass of the piston doesn't change, and for all practical purposes, and the air pressure above the piston doesn't change. So we maintain the same pressure throughout the process. So to figure out what happens, we can write the ideal gas law for the final situation. Now here, since the pressure is a constant, no subscript. The volume changed though, so we can say PV final equals NR. Those don't change here. T final. Then I can divide this by the same thing for the initial. No subscript for the P because it's not changing. V is changing now, so it gets a subscript. NRT initial. So again, we cancel out all of our common factors, and we are left with V final over V initial equals T final over T initial, which is Charles' law. And similarly, if I want to make a PV diagram of an isobaric process, in this particular one, the volume increased. So pressure, volume, I'll label my initial, my final point. The pressure never changed. So the process just looks like that. The volume increased. All right. The last of these processes that I'm going to look at for now is an isothermal process. Iso, the same, thermal, the same temperature. So this is where T is equal to a constant. So how can I keep the temperature the same? Well, I could maybe take my whole contraption here. So I'm envisioning that maybe I have a piston like so, and with a gas in here. And I'm going to float the whole thing in a very large container of ice water. So here's some water, and I've got an ice cube in there, probably lots of ice cubes. And the whole point is that this will be at 0 degrees C. If there's any net flow of heat out from, if there's any net flow of thermal energy out from the piston, it'll melt some ice. And if there's any flow in, it'll cause ice to freeze, but either way, this temperature would stay at 0 degrees C in this example. So let's say that we do an isothermal compression here. So we start at this higher volume and we end up at this lower volume. We can still do the same thing. We can write down the ideal gas law using subscripts for things that change and no subscripts for things that don't change. Now, at first blush, the way I've drawn this, you may think that the pressure is the same, but that's not the case. In order for me to get this smaller, I will have had to push down on this with my hand. That was supposed to be a hand. There we go. That's a hand. You know it's a hand because I labeled it as a hand, and I know I did the worst job ever of drawing it. Anyway, we can say P final, V final equals nRT, and P initial, V initial would also have to be equal to nRT. Well, the n's and the r's and the t's will all cancel. This is just going to be 1. So usually we rewrite this as P final, V final equals P initial, V initial, and this is Boyle's law. So what would this process look like? So the deal here is that the product of pressure and volume has to be a constant. So this means that in an isothermal process, the pressure is inversely proportional to the volume. So if I make a PV diagram, PV, I have to follow something that looks like 1 over x, basically. Man, that's a terrible V. There we go. I have to follow something that very roughly looks as 1 over x, so it's going to be something like that. Here's my initial, there's my final, like that. Don't always have to label them because the arrow makes it clear. Now the deal is that if the temperature were colder, the curve would, our process would have to fall along a curve that looked like this. And if it were hotter, so we'll say this is a low temperature, if we're hotter, it would fall along, say, something like that. And that's because the product of P and V does equal nRT. So if T is higher, the product is higher, which is going to push it up higher. Anyway, these curves here will get called isotherms in our PV diagram. Alrighty, so now historically, what happened was Boyle's law, Charles' law, Gay-Lussac's law, and some other empirical observations were all obtained by chemists and combined to obtain PV equals nRT. In future videos, we will go ahead and figure out how to get from Newton's second law of motion to PV equals nRT so that we can then think about it the way I just presented. All right, I'll catch you later.